A Boeing 747 SP parked next to any other 747 looks wrong before you can say why. Full-size wings, the same 195-foot span as the largest airliner ever built. A tail taller than a standard 747's, and in between a fuselage cut down by nearly 50 feet, as if someone took a full-length jumbo jet and squeezed it for both ends until it stopped looking like the aircraft it came from. Boeing didn't stumble into this shape, they chose it, on purpose, just a few years after finishing a decade-long campaign to convince the world that bigger was the future of flying. The 747 was the argument. Airlines redesigned entire terminals around its size. Then Boeing's own engineers took a fresh 747 airframe and made it dramatically smaller. That's not a story about a failed idea. It's a story about an idea that worked exactly as intended, and about how an aircraft can be engineered brilliantly for a problem that quietly stops existing. To understand why Boeing built this airplane, start with the one thing a standard 747 couldn't do. By the early 1970s, Pan Am, the airline that had talked Boeing into building the 747 in the first place, had found a route its own aircraft couldn't handle. The airline wanted to fly nonstop between New York and Tehran, more than 5,000 nautical miles. Even the improved 747-200 couldn't reliably make that distance with a full payload. Iran Air wanted the same route from the other direction, with a second demand attached: strong takeoff performance out of Tehran, fully loaded, in summer heat, at altitude, conditions that punish an engine and a wing far harder than a runway at sea level in mild weather. Pan Am was also eyeing something even more ambitious: nonstop New York-Tokyo, a market it believed could support roughly 200 passengers over 7,000 miles, a flight of 13 to 14 hours. Notice what kind of problem this actually was. A standard 747 could technically limp to Tehran by flying with a reduced payload, trading passengers for fuel. But that solved nothing an airline actually wanted solved. These routes were too long to fly profitably with a full 747's worth of seats, yet too valuable to hand over to fuel stops or rival airlines, what the industry calls thin routes, high value, low density, and long enough that a standard 747 burned fuel hauling capacity nobody had bought a ticket for. Nothing on the market solved this either. The McDonnell Douglas DC-10 and Lockheed L-1011, smaller wide-bodies already eating into Boeing's long-haul share, didn't carry enough fuel to make Tehran or Tokyo non-stop with a real payload. A technical stop was always possible, but it undercut exactly what an airline was selling on a flagship long-haul route: one unbroken flight, priced at a premium. And building an all-new aircraft for a market nobody was yet sure existed was a multi-year bet Boeing wasn't ready to make in 1973. So the assignment was narrower and stranger than build a longer-range 747. Take an aircraft engineered to carry as many people as possible and re-engineer it to carry far fewer, much farther, without touching the parts that were expensive to develop: the wings, the engines, the systems. Fix the range problem by removing weight, not by adding fuel tanks or starting from a blank sheet. Boeing's board approved the program in September 1973. Internally, it started as the 747SB short body, before being renamed 747SP to sell performance rather than size. Pan Am committed to 10 aircraft almost immediately, an order reported at roughly $280 million. The engineering logic is simpler than the airplane looks. Range depends on how much fuel a plane can carry relative to its own weight. The 747's wings already held enormous tanks. That didn't need to change. What Boeing changed was everything competing with fuel for that lifting capacity: the fuselage. Cut roughly 48 feet out of the body, one section ahead of the wing and one behind it, and you remove structure and weight without touching fuel capacity at all. The finished aircraft came in about 45,000 pounds lighter, empty, than a 747-200, close to the weight of a fully loaded regional jet simply deleted from the airframe before it left the ground. Every pound not spent carrying fuselage was a pound available to carry fuel instead, and fuel is what buys range. Shorten the body to lengthen the flight. That's the trade in one sentence.
But an airplane isn't a fuel tank with wings. It has to stay controllable. Think of the fuselage as a lever with the tail at the far end. The distance from wing to tail gives that tail leverage to keep the nose pointed the right way, especially at low speed or with an engine out. Engineers call it the moment arm, and shortening the fuselage by nearly 50 feet shortened it, meaning less leverage to control yaw, the aircraft's tendency to swing left or right. Boeing's fix was to make the tail work harder to compensate. The vertical fin grew about 5 feet taller, the horizontal stabilizer span increased by up to 10 feet, and the aft fuselage was reshaped and lowered. Even that wasn't quite enough at low speed, so Boeing split the rudder into 2 coordinated sections for extra authority. The result is the aircraft's signature. A fully assembled 747 SP stands taller than a 747-400, despite being dramatically shorter front to back. The tall tail isn't styling, it's the physical bill for shortening the body, proof visible from across a ramp that the range gain wasn't free.
If you're enjoying this documentary, consider subscribing. Every video here is carefully researched to bring you the real stories, remarkable aircraft, and pivotal moments that shaped aviation history. Now, let's continue.
The wing moved in the opposite direction, toward less complexity. The standard 747's elaborate triple-slotted flaps were replaced with simpler single-slotted flaps, and the bulky underwing fairings that housed the old flap mechanism, nicknamed canoes, were removed entirely. A lighter aircraft carrying fewer passengers didn't need that much low-speed lift. And then the trade-off nobody could engineer around, the one built into the whole premise. Less fuselage meant less cabin. Boeing's own 3-class figures put the SP at 276 seats against 366 for a standard 747. 90 seats gone on purpose. That wasn't a shortcoming Boeing tried to hide. It was the mechanism the airplane ran on. Give up capacity these routes didn't need in exchange for range they couldn't fly without.
The first 747 SP rolled out on May 19, 1975, 10 days ahead of schedule, and flew for the first time on July 4th with Jack Waddell, who had also flown the original 747's first flight in 1969, at the controls. It received FAA certification on February 4, 1976, and Pan Am put it into passenger service that spring, flying trans-Pacific and Middle Eastern routes much as planned. But the clearest proof of what the aircraft could do came from an airline whose need had nothing to do with Pan Am's original request. South African Airways bought 6 SPs starting in 1974 for reasons that were political as much as operational. Much of Africa had closed its airspace to SAA, forcing the airline to fly around the continent instead of over it, while also serving lower density routes the standard 747-200 didn't suit. On its delivery flight in March 1976, an SAA 747 SP flew nonstop from Seattle to Cape Town, a flight SAA's own history describes as a world distance record for an unrefueled commercial aircraft at the time. That flight wasn't a publicity stunt bolted onto the business case. It was the business case. For an airline boxed in by international politics, extreme range wasn't a bragging point. It was the only way to keep flying to London, Sydney, and New York at all. Qantas bought the SP for a version of the same original problem. Sydney to Los Angeles was long enough that a standard 747 often needed a fuel stop in the Pacific to carry a full payload, and the SP's lighter weight let the airline fly it nonstop instead. By the late 1970s, the pattern is unmistakable, and it answers a question the opening image raises. Every serious SP customer had a specific route problem that only extreme range at reduced weight could solve. A political overflight ban, a genuinely thin long-haul market, a distance that forced competitors into a fuel stop. The SP wasn't a general-purpose 747. It was a tool built for a narrow category of airline, and it worked precisely for the airlines that fell into that category. Which raises the harder question, if the airplane worked this well, why did almost nobody else buy it? Across its entire production run, Boeing sold just 45 747 SPs, a small fraction of total 747 output. The shortfall wasn't a mystery of taste, it was arithmetic that didn't work outside a narrow set of routes. The SP burned somewhat less fuel than a full-size 747, it was lighter after all, but nowhere near a quarter less. It still flew on 4 engines, with a full-span wing and nearly the same drag as its larger sibling. Spread that fuel burn across a quarter fewer seats, and the SP's cost per seat came out meaningfully worse than a standard 747's on any route both aircraft could actually fly. The SP was never built to compete on cost per seat. It was built to fly missions nothing else could fly at all. The instant a route could be served by a standard 747 or by a cheaper trijet, the SP lost the comparison. And most of the world's long-haul network could, in fact, be served that way. Even Pan Am, the airline whose request had started the whole program, felt this math directly. It had originally signaled interest in as many as 25 aircraft, but under financial pressure, ultimately took only its original order of 10. Qantas, an early enthusiast, took just 2. Orders across the industry settled into small specific batches rather than a fleet standard anywhere, exactly what you'd expect from an aircraft that solved a real problem for a short list of airlines and nothing for everyone else. Boeing's own retrospective points to a combination of causes: continued improvements to the standard 747-200B narrowing the SP's range advantage, U.S. airline deregulation reshaping route networks, and escalating fuel prices through the late 1970s, each of which shrank the narrow slice of missions where the SP alone made sense. Deregulation in particular restructured how U.S. carriers built their networks, pulling traffic through hubs rather than flying point-to-point on thin, long routes, quietly reducing the number of Tehran problems left to solve. The final regular production 747 SP was delivered to the Iraqi government on August 30th, 1982, just 9 years after the board approved the program. That closes the commercial half of the story, but not the deeper one. The SP didn't lose to a specific rival. It lost to a moving target, a set of forces that kept narrowing what only it could do, until almost nothing was left that only it could do.
The single biggest reason the SP's market kept shrinking had nothing to do with the airplane and everything to do with regulation. When the 747 SP was designed, a twin-engine jet was legally barred from flying more than 60 minutes from a diversion airport, a rule from an era when engine failures were common enough to make that caution reasonable. That 60-minute limit is a large part of why oceanic long-haul flying belonged almost entirely to 4-engine aircraft like the 747 and 3-engine designs like the DC-10 and L-1011 in the first place. Through the late 1970s and into the 1980s, jet engines got dramatically more reliable. Fewer in-flight shutdowns, longer intervals between overhauls, better monitoring. Boeing spent years feeding the FAA that reliability data, pushing for an exemption for its new twin-engine 767. Regulators followed the evidence. In January 1985, the FAA extended the maximum diversion time for twin jets to 120 minutes under what became ETOPS. And on February 1, 1985, TWA flew the first ETOPS 120 transatlantic service, a 767-200 from Boston to Paris. Pan Am followed the next year, opening its own transatlantic twin-jet service with the Airbus A310. This is the change that actually undercut the SP's reason for existing, not because a rival airplane beat it in a head-to-head sale, but because it solved the SP's exact underlying problem from a completely different angle. The SP existed to deliver 4-engine range and reliability on a lighter, smaller frame. ETOPS gave airlines oceanic clearance on an even smaller frame, 2 efficient engines instead of 4, without giving up a single seat to get it. A twin jet burning fuel for 2 engines, now legally free to cross the same ocean, beat the SP's economics on almost every number an airline's finance department cared about. The aircraft that fully capitalized on that opening had to mature first, and that took another decade. The Boeing 777-200 entered service in 1995 with a range around 5,240 nautical miles and typical seating over 300. Long range and high capacity in the same airframe, with none of the SP's trade-off. Airbus's A330, introduced around the same period, offered comparably long range on 2 engines.
Once aircraft like these existed, an airline chasing a genuinely thin, ultra-long route no longer had to choose between a full 747's capacity or the SP's shortened compromise. It could simply order a twin size correctly for the market from the start. The specialization the SP had built by subtraction was now a standard factory option at a lower cost per seat. Even the standard 747 kept closing the gap from its own side, as later variants steadily extended range while keeping full seating capacity, eroding the one thing that had once belonged to the SP alone: long range at reduced weight. No single force killed the SP's market. Rising fuel prices made its seat economics worse. Deregulation reduced the number of routes shaped like the ones it was built for. Improving standard 747s closed a range gap from above. ETOPS cleared twins closed it from below, at lower cost. Later, long-range twinjets closed it from both directions at once. The SP wasn't beaten by any single competitor. It was surrounded, slowly, by an industry solving its exact problem cheaper than a shortened 4-engine jumbo ever could.
Retired from mainline service, a number of SPs kept doing versions of the same work that had justified building them. Long, uninterrupted range for missions ordinary aircraft couldn't manage. Several went to Middle Eastern governments as VIP transports, valued for exactly the qualities Pan Am and Iran Air had asked for originally, crossing continents without a technical stop on an airframe small enough to operate flexibly. The most striking second life belonged to a former United Airlines SP, converted by NASA and the German Aerospace Center, DLR, into SOFIA, the Stratospheric Observatory for Infrared Astronomy. Engineers cut a large door into the fuselage and mounted a 2.7-meter reflecting telescope inside, designed to fly into the stratosphere, as high as roughly 45,000 feet, above about 99% of the water vapor that blocks infrared observation from the ground. The choice of airframe wasn't incidental. The 747 SP's tall tail and lightened structure had been built in 1976 to climb high and fly far on a route between continents. In 2010, those same qualities let it climb above nearly all of Earth's water vapor to see the infrared universe clearly. SOFIA flew its first science mission in 2010 and its final flight in September 2022, an airframe originally engineered to carry paying passengers, instead carrying astronomers to the edge of the atmosphere. By the early 2020s, most of the handful of 747 SP still flying were government or VIP transports, alongside two kept in service by Pratt & Whitney Canada as engine testbeds. The aircraft that once flew fare-paying passengers nonstop between continents now survives almost entirely as a specialist tool, valued for precisely the trait that made it strange to begin with: an unusual amount of performance packed into an unusually small frame.
Go back to that first image, a 747 with the middle missing. Wings and tail sized for a giant, body sized for something else entirely. The instinct is to read that shape as a mistake, a jumbo that didn't quite come together. That reading has it backward. The 747 SP wasn't a smaller 747. It was a precise answer to a precise arithmetic problem. A handful of routes too long and too thin for any full-size aircraft to fly nonstop with a paying load in an era when only 4 engines were trusted to cross an ocean alone. Every strange proportion on the airframe, the tall tail, the split rudder, the missing rows of windows, is the visible record of Boeing solving that problem well enough to set genuine distance records doing it. What changed wasn't the airplane, it was the size of the problem. Engines got more reliable. Regulators let 2-engine jets fly the oceans a 4-engine SP had once needed to cross alone. Fuel prices punished its seat economics. Deregulation reshaped the routes it had been built around. And newer aircraft eventually delivered its range without its trade-off, at a lower cost per seat. None of that happened because the SP failed. It happened because the SP succeeded narrowly enough, and specifically enough, that once the industry found cheaper ways to solve the same problem, there was nothing left that only a shortened 747 could still do. Not a compromise that never worked. An engineering answer so precise that when the question changed, there was no smaller 747-shaped question left for it to answer.